So up until now, we've looked at different ways that we can differentiate different equations. So we can find the gradient of specific points on a curve. Because we know with a curve, the gradient is always changing. So if we want to find the gradient at any point, we needed a way to create a function of the gradient in order to calculate those values. Now, if we go back to IGCSE, and we think about before we were able to find the gradient of a specific point using differentiation, the only way that we could find the gradient for a specific point on a curve was by approximating it with a tangent, because the tangent at that point, it has the same gradient as the curve at that specific point. So what I've drawn here is the tangent. Right, this is the tangent at this point, and let's give this point some coordinates. Let's say it's x1, y1. So this can now work backwards for us. If I could find the gradient of a specific point on the curve, I could use it to then calculate the gradient for the tangent. In fact, they would be the same. So if I could find the gradient, and to do that, I'd differentiate to find the gradient function, which is dy on dx. If I put an x coordinate into the gradient function, it would tell me the gradient at that specific point. And the tangent happens to go through that point as well. And so the gradient of the function at that point is also the gradient of the tangent, which we normally represent as m, coming from our straight line equations. Now, another line we're going to meet is something called the normal. So the normal is perpendicular to the tangent. It also passes through the same point that the tangent passes through on the curve. Now, if we remember back to our coordinate geometry, the gradient of a line perpendicular, if you multiply their gradients together, you should get -1. And so a line that is perpendicular has a gradient that is exactly the reciprocal and also the negative. So it would be -1 over whatever the gradient was for the tangent. So this now allows us to come up with an equation, a straight line equation for the tangent and the normal. So if I wanted to find the straight line equation for a tangent at a specific point, we learned this new equation, y minus y1 is equal to mx minus x1. So x1 and y1 being some point on the tangent, and m being its gradient, and its gradient being the derivative at a specific point on the curve. Now, for a normal, if we want to calculate the straight line equation for the normal, it would be y minus y1 equal to, but we need to change the gradient. This is the perpendicular line, so its gradient would be -1 over m x minus x1. So here we have two equations that we should memorize when we're dealing with tangents and normals. So let's look at this in practice. Here we are asked to find the equation for the tangent and the normal to the curve, and here's the curve. So in order to calculate the straight line equation for a tangent, it's y minus y1 equal to mx minus x1. I need a coordinate and I need the gradient. Now I only have an x coordinate for where the tangent is, right? And I need a y coordinate. Now fortunately this is an equation of y equal to, so I can put 2 into the equation and it will give me the y coordinate. Then I also need the gradient, right? And we know now that if I'd like to calculate the gradient for the tangent, I can differentiate the function and I can calculate what the gradient is at x equal to 2, and it will tell me what the gradient is. Okay, and the gradient at the curve at that point is the same as the gradient for the tangent at that point. Now for the normal, if I want to calculate the equation for the normal, we can use the same point because it passes through the same point, except this time it is just the negative reciprocal of the gradient and everything else is the same. So it doesn't really matter which one you do first, but what I'm going to do first is I'm going to find the y coordinate. So I'm going to put x equal to 2 into the equation. So I'm going to say when x is equal to 2, y is equal to 3 times 2 squared minus 2 plus 8 over 2. And this is going to give me 14. So now I have a point. I have the point 2, 14. So now I can find the gradient function, the derivative. So in order to find the derivative, I'm just going to rewrite this equation quickly in a format that I can differentiate. So I need to bring all the powers to the top. So 8 times x to the power of minus 1. And now I'm just going to find the gradient function using the power rule. Okay, so a nice simple derivative here. So we'll get 6x minus 1 multiplied by the power. So this will become minus 8. Reduce the power by 1, it will become x to the power minus 2, which is just over x squared. Now this is an equation for the gradient function. What it does is I put x coordinates in and it tells me what the gradient is at that point. So I'm going to ask, what is the gradient when x is equal to 2? So at x equal to 2, dy dx, which is the gradient, is equal to 6 times 2 minus 1 minus 8 over 4, and that is 9. So the gradient at x equal to 2 is 9, which means that the gradient for the tangent at that point is 9. And so I'm ready to write my two straight line equations. So for the tangent, we'll have y minus the y coordinate of the point, which is 14, equal to the gradient, which was 9, x minus the x coordinate, which was 2. And if the question doesn't ask me to simplify or use the equation in any way, I can leave the equation like this. So for the normal, we have y minus 14 again, because it's the same point, equal to, this time it is the negative reciprocal of the gradient for the tangent, so minus 1 over 9 x minus 2. And that is the equation for the normal. So here's the tangent, and here's the normal. Right, and again, if we're not asked to use this equation or simplify it anyway, we can leave the equations as is. So just to get a sense of what we've just done, we can quickly hop into Desmos. This is the equation for the curve that we've just been looking at. So this is the graph of 3x squared minus x plus 8 over x. And if we want to see, there's our equation for the tangent at x equal to 2. And here is the equation for the normal at x equal to 2. Now it looks a bit off 90 degrees, mainly because I've changed the scale of the axes so that I can show more of the graph, right? But that is essentially what we've just found. We've found the 2 points, right? One or two straight lines. One, the blue one is the tangent and the green one is the normal. Okay, let's hop to our next example. Here we are told that the normals to the curve of this cubic equation at the points A and B meet at point C. So the normals are two straight line equations, and when two straight lines meet, they meet at a specific point, and that point happens when the two lines are equal to each other. So our first goal is going to be to find the equation for these two lines. So I need the equation for a normal. Okay, so to calculate the equation, the straight line equation for a normal, it's y minus y1 equal to minus 1 over m, m being the gradient at that specific point on the curve, x minus x1. So I have both points of both normals, so I don't need to go find a point, but I don't know the gradients at those points. So what I'm going to need to do is I'm going to need to find some gradient function for this curve so that I can find the gradient at those specific points. So I'm going to differentiate, and this is just a sum, so I'll just differentiate using the power rule. So we'll multiply by the power, reduce by 1, multiply by the power, reduce by 1, multiply by the power, reduce by 1. And 1 is a constant, so it doesn't differentiate. Okay, so I'm going to have to put two different values in here because I want the gradient at 2 different points. So we'll start off with point A first. So at point A, the x-coordinate is 4. So we'll say when x is equal to 4, then the gradient is equal to 3 times 4 squared minus 10 times 4 plus 3, and we'll get 11. And at point B, that is when x is equal to 1. So when x equals 1, then the gradient is equal to 3 times 1 squared minus 10 times 1 plus 3. And that's going to give us minus 4. Okay. Now that's not the gradient for the normal. That's going to be the gradient for the tangent. So that's important to remember. This is the gradient for the tangent because the gradient for the tangent is the same as the gradient for the curve at that point. Now, fortunately, our equation for the normal takes care of all of that, right? It makes sure you put the gradient in the correct place and make sure you use the right equation. So the equation for the normal that passes through A will be y minus 3. That's why you always put your negative numbers in substituting in brackets, equal to minus 1 over m, which we've worked out to be 11. And here we will have x minus 4. So this can be equation 1. And the equation for the other normal is y minus 0 is equal to minus 1 over, this is going to be minus 4, x minus 1. Okay. So obviously in this equation here, these things are going to cancel out and we're going to get a positive gradient. So this could be equation number 2. So in the previous example, you noticed I left the equations as is, right? Because we had no further application for them and we weren't asked to give the equation in any specific format. However, this time we need to equate these equations, so we can either do that by substitution or elimination, but in either case it might be easier to change these equations to something that is a little bit more easier to read. So we're going to take equation 1 and multiply that 11 away. So we're going to get 11y, we're going to get plus 33 equal to, and I'm going to multiply that minus 1 throughout the bracket, I'll get minus x plus 4. And now I can just rearrange and I'll get 11y is equal to minus x minus 29. So this can be now a new one, perhaps equation 3. You could have done this beforehand already, so you could have done this in this step already, preemptively thinking about where we were going. Right, then we'll take equation 2 and do exactly the same thing. I'll just multiply everything by 4, so I'm going to get 4y equal to x minus 1. That's good enough. We'll call that equation 4. I can just add these two equations together and the x's will go away. So I'll take equation 3 and add equation 4. So in other words, 11y equal to minus x minus 29 plus 4y equal to x minus 1. So I can add the two equations together, and that's going to give me 15y equal to minus 30. So y must be equal to minus 2. And now I can just substitute back into either equation and I can find the x-coordinates. I'll use equation 4. So 4 times minus 2 must be equal to x minus 1. So that means that x has to be equal to negative 7. So point C is the point minus 7, 2. And we can illustrate this again by having a look at the graphs on Desmos. So we can pull up the cubic equation. So here's the cubic equation that we've just looked at. Here's the equation for the normal at point A. Here's the equation for the normal at point B. And we can see that they meet, if we change the scale back together to normal, that they meet at this point here, and that point with the black and red lines cross we can see is the point -7, -2. Now, the next part of the question said find the area of the triangle. And to find the area of the triangle, we can use that special stitch method to using the 3 coordinates. We can string them together and you could find the area. But that's not required for additional maths examination. That's just something extra that you're taught that would make life a little bit easier.